Stavros now?
Mm-hmm.
Good. So, yeah, you've seen my talk, and here is my abstract, and since you've already read it, I don't need to read it to you again. But here is, and also I should say that my talk follows a handout, so each of you should be facing one. I hope you all have one. I think you don't. So here is your copy. And I should say that it's an ideological point. I think talk should come with handouts, because what if I want to review what you said, Ilya, for example? And second, talks should come with a video, and it should be the responsibility of the organizers to tape everything, because, you know, 1 in 10 talk is worth going back to. For me, 1 in 20, but even if it's 1 in 20, it's worth taping all the rest, because you don't know which one it will be. And here is my abstract in a slightly less abstract form. What I'm going to tell you is that a certain collection of operations, when you restrict your attention to a strange Lie algebra, is included using a funny inclusion. This is an inclusion symbol right here, inside a category with a weird definition and a name that Christian summarized as blah blah, and I call it DoPeGDO for docile perturbed Gaussian differential operators, and I will explain it later. But before that, I should say that not theorists should rejoice, should be happy about it, because it leads to a very well-behaved knot invariants which have good properties. Okay, so it's more than that they are powerful. They are extremely powerful, but they also have good properties, and they are computable in polynomial time. So, you know, you can actually compute them in principle for very large knots. And quantum algebraists should be happy, because it's a realistic playground for testing complicated equations and theories, and I will show an example later. But before I really start, thank you for inviting me to DaNang. My talk, including the video, will be on the web, which is, and omega epsilon beta is defined to be http://drawbn.net/v19. So there are also a few links within the handout which all start with this. For example, there are other talks that I gave, and they are at web/talks. And I should also say that everything continues work of Rosansky and Overbay, and is joined with Roland van der Veen. And I should also, sort of an old version of this talk 2 years ago, and I knew a lot less, I was much more blunt. And my title was, whether or not you like the formulas on this page, and they are hard. You're not necessarily going to like them. You can't ignore them, because they describe the strongest truly computable knot invariant we know. And again, back to my overall scheme. Lots of operations for some specifically algebra are included in a funny way in a category blah blah. Okay? So first of all, what are the operations? So given so in quantum algebra, you often encounter situations where you have a space U, a vector space U, often called a universal enveloping algebra or a quantized universal enveloping algebra. And I actually mean both of them in this case. So either a universal enveloping algebra or a quantized universal enveloping algebra. And it is equipped with a number of operations. So first of all, it's an algebra. So it's equipped with a multiplication map going from U tensor U into U. And in fact, not theoretically, I also want to tell you what each of these operations corresponds to in knot theory. Okay? So knot theoretically, this operation corresponds to taking a tangle that has two components, or maybe more, but anyway, you single out two of them and you connect them to each other so as to have a single component instead of two, a single longer component. That's what the multiplication corresponds to. Then there is an operation called the coproduct, which goes from U to U tensor U, and not theoretically it corresponds to taking a strand, which is really a narrow band, and using scissors you cut it in the middle, so now you get two copies of the same strand that trace the same root. There is the antipode, a map from S for S going from U to U, which really corresponds to reversing a strand and adding, just to be annoying, just to make life hard, it also adds a mu at the top and a ka at the bottom. Then there is a trace operation, which takes a component, algebraically it's the projection from the algebra to its coinvariance, and not theoretically it corresponds to taking one component and closing it into a closed component. So taking an interval in a tangle and closing it to a circle. This is the only operation in my diagram here where I've put a question mark, because this one I'm actually not sure it's DoPeGDO. I have very strong evidence that it is, but the work is not completed. Then there is the crossing. The crossing is an element of U tensor U, except here it's not the general U, but it has to be the quantized U. So there is an element of QU tensor QU, which represents the crossing. Then there is the Ka and the Mu. Then there are associators. So an associator is somehow something that changes the bracketing from things being left bracketed to being right bracketed, and it's shown in green here. And again, I'm also claiming it's DoPeGDO. Then there is the value of the vertex. So it turns out that in certain circumstances, you can write an associator as a product of 4 vertices, and each vertex is DoPeGDO 2. I still haven't defined what's DoPeGDO, but I'll get to it. And finally, there is more. So there is a Cartan involution, there is a dequantizator, and there is even more than that. And all of these things are DoPeGDO if you're wise about the choice of Lie algebra. So now let me tell you about how to choose the Lie algebra. Okay?
And
so,
CU?
What?
You said that QU is the quantized, and what is CU?
CU is the classical algebra. So U is a name for an algebra in general, sort of a type of algebra. CU is the classical version, just the universal enveloping algebra, and QU is the quantized version. Okay?
George?
Yeah?
So the difference between this and like the Reshetikhin-Turayev tangle factor is that you have vertices, is that right?
That's one of the differences. I also have lots of operations. In fact, it's defined in a slightly more general context. Reshetikhin-Turayev tend to depend on having representation theory. I don't care about, I dislike representation theory. I don't want representation theory. So this is more similar to, what? What?
Don't say this to us. It's like you tell me.
Yeah, I know, it's blasphemy. Sorry, that's my nature. This is more similar to the Ochtsuki universal invariant, which is valued in one copy of the universal of the quantized algebra per strand.
Okay.
Okay? No choice of representation. That's important. No representations. Okay. Anyway, so all of this is happening for one specific type of Lie algebra, so let me explain. So the area surrounded here in brown is supposed to represent the world of all two-dimensional Lie algebra. So a four-dimensional Lie algebra. So if you have a four-dimensional vector space, you can put a bracket on it. A bracket is a map from the vector space tensor itself to itself, okay? And sometimes this bracket will be a Lie algebra bracket. Sometimes this multiplication map will satisfy the Jacobian, the axioms of a Lie algebra. So you get a variety which describes all Lie algebras, and this is a schematic description of this variety. In this variety, there is a special point, the bracket, the zero bracket here, and it corresponds to abelian Lie algebras. If you look at the generic point in this variety, it turns out to be isomorphic to SL2 plus a one-dimensional extra component, because it's four-dimensional instead of three. There is also a certain high codimension subvariety in which you're looking at solvable Lie algebras. So my story happens around one specific solvable Lie algebra over here, and it involves a path of Lie algebras called SL2 plus up epsilon. So when epsilon is equal to 0, the path is at the initial point, and the algebra you're looking at is solvable. When you increase epsilon, you go outside of the world of solvable Lie algebras and into the world of algebras isomorphic to SL2 plus one-dimensional, hence the name SL2 plus. The plus means this extra one-dimensional component. Okay? And really, everything that I will do will be to expand this universe of operations that I alluded to before as a power series in epsilon and understand everything that happens right there. So, namely, I will understand what is happening in a neighborhood of this red point. Okay? And if you want to compare it with a possibly more familiar situation, Vasiliev invariants correspond in exactly the same way to expanding the world of Lie algebras around the commutative Lie algebra. Okay, so that's the Lie algebra that I will be talking about. But of course, it becomes generators and relations at the end. So here it is. SL2 plus epsilon is the Lie algebra generated by four generators, y, b, a, and x. So y and x are the ordinary sort of off-diagonal generators of SL2, and b and a are the two competing elements for the Cartan. It's sort of one dimension too much. And the relations are the commutator of A with X is X, the commutator, oh God, I'm not going to read this to you, you can read it yourself, various commutation relations. If you look at it carefully, you notice that the element T, which is equal to epsilon A minus B, is central. So you can mod out this Lie algebra by the central element, and if epsilon is invertible, I think I forgot this if in your handout, in the copy of the handout that you're holding, but it's necessary. So if epsilon is invertible away from epsilon equals to 0, if you mod out by this central element, you get the ordinary SL2. So this is just to explain the naming, the context, okay? And then the algebra U that I'm talking about is either CU, which is the completed universal enveloping algebra, or QU, which is a quantized version thereof. And the quantized version is written here. The commutation relations are written here. And in fact, I should say that one has to make a quantum leap and actually quantize everything to get QU. And in particular, the coproduct, instead of being the naive coproduct of CU, becomes this coproduct. So the delta of y is y1 plus b1 y2, meaning y in the first component plus b in the first component times y in the second second tensor factor, where b is defined here. It's it's defined here. Okay, and so on. And again, the details are not really important. I'm not going to get to them anyway. And I should add that there is also an R matrix, and the R matrix is sort of similar to R matrices that you see in quantum algebra, or in fact, it is the same as what you see in quantum algebra. So it's sort of an exponential, but with quantum integers quantum factorials instead of our ordinary factorials. So a quantum exponential. Okay, yes.
I'm sorry, I'm confused with the notation. What does this, why are there 4 entries in delta? What are the 4 entries?
No, this is delta of y is equal to this.
Oh.
Delta of b is equal to this.
Yes, okay.
I thread delta over a list.
Excellent.
Okay? And I suppose I have to tell you what's the right-hand side. So what's the category blah blah? So first of all, a few conventions. Given any set A, I let Z sub A be a set with a set of variables that I will use later. And the variables are called Z sub I, where I belongs to A. And every variable in my story will always have a dual variable. So the dual of every Latin letter, later I will also have other Latin letters like Y and X, but the dual of every Latin letter is the corresponding Greek letter. So the dual of Zi is zeta I. So zeta sub A will be the collection of all zeta I, where I runs over our indexing set. That's just a convention. And the other convention is that everything converges. So you're not allowed to ask me questions about convergence, only for the purpose of saving time. Okay? Good. So what's DoPeGDO? Or blah blah again, sorry. So what's DoPeGDO? DoPeGDO is the category whose objects are finite sets. And you'll notice that there is a symbol here of a footnote, because this is a simplified definition of DoPeGDO, and the complete definition is given in the footnotes. But you really want to understand just the simplified version. Everything else is just extra complexity. Okay? So, and then the morphisms from a finite set A to a finite set B are elements that I'll denote by the letter F, and they are those docile, perturbed Gaussian differential operators. And they look like a scalar times the exponential of a sum of two things. All of these things are power series, omega, the scalar is a scalar, but Q and P are certain elements or power series in the ring of power series in the variables, the Greek variables corresponding to the input and the Latin variables corresponding to the output, with further constraints. So omega is a scalar, again with a footnote. Q is a small quadratic in all of the variables, both the Greek inputs and the Latin outputs. And the word small is the fee that I'm paying to convergence. So it's small so that the exponential of Q will make sense. But I'm not telling you what exactly I mean by that at this point. Okay? And P is a perturbation. So if you've seen quantum field theory, it's very similar to Lagrangians. Okay? You have a quadratic part and a perturbation part, except that I want the perturbation to be docile. What does docile mean? It means that, well, everything is a power series also of epsilon, in the variable epsilon. Q does not depend on epsilon, P does depend on epsilon, and epsilon is the same epsilon from before, from the parametrization of SL2 plus epsilon. and I want P to be a docile power series, which means that it's a sum as k is greater than equal to 1 of epsilon to the k. So it's always proportional to epsilon. There is always an epsilon term because k is greater than or equal to 1. And then it's epsilon to the k times p to the k, where the degree of p to the k, p up k, is less than or equal to 2k plus 2. Okay? So docile means sort of the degree of p of the kth perturbation term is bounded. Okay? I should tell you about compositions. So the way you compose two such elements, so by the way, the notation double slash means composition done in the correct order. So F goes first and G goes second. What is normally, what people often denote as F, as G circle F. Okay? So F circle G means you take F and you replace all the Latin letters in it. The Latin letters are the letters corresponding to the target space. So you replace all the Latin letters in it by differentiations with respect to the corresponding Greek letters, to the dual variables, and you apply the differential operators that you get here to G. G will have corresponding Greek letters because G will be going from, if F went from A to B, then G will be going from B to C, so that you can compose them. And so the Latin letters of G will be, the Greek letters of G will be the letters will be corresponding to B. So these zi's, these zeta i's can differentiate elements in G, can differentiate the variables appearing in G, and then you substitute all the Greek letters in the middles. So all the zeta i's, where the i's are in B, you set them to 0. And this, by the way, can be written in the opposite way as well, but one way is enough.
So, Dror?
Yeah?
You don't assume that Q is non-degenerate, the quadratic?
I do not assume that Q is non-degenerate,
So
no.
It could be 0.
Q could be 0, yes.
Oh, okay.
And in fact, it still makes sense. This is not Gaussian integration. This is Gaussian differential operators. It's something else.
Okay.
And this, so I think the parts of the name are explained, okay? So differential Gaussian, what is clearly seen here, perturbed is seen, docile is seen, and differential operators is how composition is defined, okay? Maybe I'll quickly go through the footnotes just to explain that things are actually slightly more complicated. So, but sort of in the way we standardly make mathematics more complicated. It's not so unusual. So each variable has a weight. So really we're talking about graded degrees, graded variables, okay? And the weights are always either 0 or 1 or 2. And we always have that the weight of a Latin letter plus the weight of the corresponding Greek letter is equal to 2. So really the sets are not ordinary sets. When I talk about finite sets A, they're not ordinary sets, they're graded sets. So each set A decomposes into a disjoint union of A0 corresponding to variables of weight 0, A1 corresponding to, well, and so on. And really, when I say a scalar, I mean a power series in the weight 0 variables. The weight of the quadratic must be 2, so in fact you can decompose it as a Q20 part, so and a Q11 part. And the coefficients of Q20 are, you know what, I'm not sure I want to really read all of this to you. These are really technicalities. Okay, of course, without the technicalities, everything is false, but there are still technicalities. You know, maybe the last thing is that if you set the weight of epsilon to be -2, then to be docile, is to have weight less than or equal to 2. And maybe one last thing, there is also an obvious product, not composition, just product. So if you have a morphism from a finite set A1 to a finite set B1, and another one from A2 to B2, you can simply multiply them. If you multiply two quadratics, you again get a quadratic. If you multiply two perturbed quadratics, you get a perturbed quadratic. So you get a morphism with all the going between sort of the unions of the sets of variables. And again, there's still a lot to say, okay? But even before that, what is so cool about it? So what is so cool about what I did? You have to contrast it with representation theory. So in representation theory, if you have a homomorphism from one tensor power of a representation to another, so if you have an element of V dual tensor to a set sigma, a tensor V to a set S, then the dimension of this space of homomorphisms explodes. This is a space of an exponential size. And this is the kind of spaces that you encounter if you work with Reshetikhin-Turayev or with skein modules. Sorry. And these spaces grow in size so quickly that in practice you can compute things only for relatively small knots. And the more modern things become, the smaller the knots that we can actually compute them on are. Okay? However, in our case, so sigma and S will correspond to the sets A and B that I will that I mentioned before in the definition of the category. So if the sizes of A and B grow, then the space of quadratics over variables corresponding to A and B also grows, but it also only grows quadratically. The number of quadratics, well, a quadratic is just a matrix, so its size is the square of the number of variables. So the space, so basically the size of DoPeGDO is way smaller than the size of the things that you have to look at in representation theory. And likewise for bounded degree polynomials. So if you look at docile polynomials and crop them at a certain power of epsilon, so if you look only at up to epsilon to power 3, say, then you're looking at polynomials of degree, what is 2, 3 plus 2, whatever it is, I mean some finite degree, and polynomials of a finite degree grow slowly. The dimension of such space grows slowly in the number of variables. So everything is computable in polynomial time as opposed to representation theory, which explodes. And that's the main reason why all of this is very, very cool. And this is just to be provocative. Okay, can I continue? So you see, I owe you lots of things, and maybe the first, maybe the first of them is roughly how the inclusion goes. So I should only say one thing, that if you have a homomorphism from U to the sigma to U to the S, then it corresponds to a DoPeGDO which goes from sets which are 4 times the size of sigma and 4 times the size of S. So really there isn't just Zi's and zeta i's, but you have eta i's, beta i's, alpha i's, and xi I, ignore tau for now. And also yi, bi, ai, and xi. So really, again, a homomorphism maps to a DoPeGDO map between sets of 4 times the size. But again, that's a linear expansion. That doesn't change anything for computational complexity. And yes?
Does DoPeGDO has any structure like graded category or something?
No. No. It's not graded. Okay? But it has a composition. And I didn't yet tell you how to compose. I told you that composition is defined by composing differential operators. What is hard is to understand why is it that the composition of 2 differential operators of this kind is again a differential operator of that kind. So why is it that when you compose 2 Gaussian differential operators or perturbed Gaussian differential operators, the result is again Gaussian or perturbed Gaussian? And that's my next slide. And perhaps this is the most important slide. So suppose you have a morphism in DoPeGDO from A to B, from a finite set A to a finite set B. Then, first of all, a morphism involves a quadratic, right? And a morphism will have a Q part, which is a quadratic, and it's a quadratic in all variables. So it will have a quadratic which involves 3 types of terms: mixed zeta z, mixed Greek-Latin terms, Greek-Greek terms, and Latin-Latin terms. And the coefficients of each such type will be a matrix. So there will be a matrix EIJs of coefficients of Greek-Latin, a matrix FIJ of coefficients Greek-Greek, and a matrix GIJ of coefficients Latin-Latin. So I will draw such a morphism as, so there will be an input side of Greek letters, an output size of Latin letters, and then there will be a matrix E connecting the Greeks and the Latin, a matrix F connecting Greeks to Greeks, and a matrix G connecting Latin to Latin. But in fact, if you look at the morphisms, they also have a scalar part, which I will put at the top, and also a perturbation part. And the perturbation part can have both Greek and Latin letters. So it will be some high-degree polynomial that has a side on the Greek and a side or some variables on the Greek side and some variables on the Latin side. Now, suppose I have two such gadgets. So this is just a graphical notation for omega e to the q plus p. Okay? So suppose I have 2 such gadgets, one with numbers 1 and the other one with subscripts 2, and I want to compose them. Compose means, well, if you look at the definition of composition right here, it means replacing all the Latin letters here by differential operators, by differentiations, and acting on all the corresponding elements here, and then substituting for everything, for whatever remains, substituting these letters to be 0, these variables to be 0. Okay? But the way d to dx acts on x is, well, the 2 pair and cancel each other. Okay? So really we are schematically, we are summing over all ways of connecting the ends here to the ends here. Okay? Such that it's a perfect match, such that nothing is left over, because if anything gets left over, if anything is left over, it gets killed by the substitution. Latin letters go to 0, which we make at the end. Okay? So really, I have to figure out how to make all possible connections of things here with things, how to compute all possible pairings of things here with things here. But also remember that sort of each of these kind of little edges here really corresponds to an exponential. I'm not talking about quadratics, I'm talking about exponentials of quadratics. So really you should be thinking of like each such arc as repeated many, many times, say k times, with a coefficient 1 over k factorial and a summation over k. So I want to compose two such gadgets, and the claim is that the result is a gadget of the same type. So how do you do that? So basically, when you compose, you end up pairing an end here with an end here, or maybe you will be pairing this with that, or maybe you will be pairing this with one of the variables that appear in the perturbation term. But again, remember that this arc is repeated many, many times. So you do, so I mean, even if you pair one instance of it with something here, you still have many copies to continue playing with. Okay? So you'll get all sort of long arcs where you start from here, say, connect to an F term, then connect back again to a G term, then connect back again to an F term, then possibly connect to an E term. And you have to somehow figure out what are all the things that you can get. So, for example, let's figure out what are all the ways after you compute the composition to get from the left to the right. In other words, what is the E term of the output? The E term is the term that goes from the left to the right. Sorry, without touching the perturbation in first iteration. So if I want to get from the left to the right, so from the left to the right using this composition, then I have to start here, go to the right, then possibly connect to an F, then possibly connect back to a G, then possibly connect again to an F, then possibly connect again to a G, and eventually, so do a loop of FG, 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 and eventually come out of this loop via an E2. So maybe I'll write it as I wish I had, oh, here. Sorry, can I use this on the paper? Oh, sorry. So I'll get things that look like E1. So E1 is getting from A to B. Then maybe no connections at all with F's and G's. So maybe I will connect directly to E2. So maybe E1 will be multiplied directly by E2, meaning I'll put here an identity. But maybe instead, from E1 I will connect to F2 and then to G1 and then to E2. So I'll also have a term here, F2, G2. But maybe I will be doing this middle part. Maybe I will be doing this looping part twice. So I'll be getting here F2, G2 squared. But you know, maybe I could do it any number of times. But this is a geometric series. What? Oh, G1, sorry. But this is a geometric series, and the sum of the geometric series is E1 times 1 minus F2 G2 inverse E2, and I believe this is what sorry, again, E1, F2 G1, and I believe this is what I wrote here. So the E of the output will be E1 times 1 minus F2 G1 inverse times E2. Okay? And similarly, the F of the output, so F means starting from the left, coming back from the left. So starting from the left, coming back to the left, you could first do an E, then do a looping of F2s and G1s, and then come back using another E. So, so this is the F of the output, written in a similar way. This is the G of the output. And you can also simply loop. So you can have a loop of F1s of F2s and G1s, which closes on itself, and you can check that it contributes a determinant factor. And so here is a complete description of the omega, E, F, and G part of the output. Now, if you don't believe me, you can simply forget all the rationalizations that I gave you and take it as a definition. This is the definition of composition in DoPeGDO. Yes?
No, I don't understand this. Each rectangle should represent a function of finite sets, correct?
Each rectangle represents a power series in variables corresponding to zeta A and ZB.
But aren't we in a category where objects are finite sets?
The objects are finite sets, but the morphisms are quadratic, are power series which have a description as differential operators. Or yeah.
Very good. So can you repeat now again what should be the output? What should be the output?
Okay.
Of the rectangle?
So if the input, so let's ignore the perturbation for now. So let's describe the non-perturbed version. So if the input is a scalar times a quadratic, which decomposes into three types, into three parts. So sorry, this is the one morphism of the input, and the second morphism is again a scalar times a quadratic, which decomposes into three parts. Then the output will be a scalar times a quadratic. Oh, this should not be a Q1, this should be a Q.
Yeah.
So the output should be a scalar times a quadratic, which decomposes into three parts. And the new scalar is the product of the old scalars times a certain determinant. The E part of the output quadratic is given by E1 times 1 minus F2 G1 inverse E2, and so on. Okay? So this is, again, admittedly complicated formulas, but they are right. They work. Okay? It actually defines an associative composition.
So
Okay?
Paul,
Yeah.
So here you assume, I guess, that the F and the G's are small.
So I'm assuming that things are small so that the composition will make sense, and I forbade you in the beginning from asking this question. This is convergence. Okay?
Yeah, it's the vanishing of the determinant.
No, it's not the vanishing of the determinant. It's basically things are so.
Yeah.
So, you know, power series have to converge. There has to be a reason for it, and I'm not telling you what it is. Okay? But it's a technical point. But you are right. Strictly speaking, what I wrote is nonsense because these matrices may not be invertible. But if things here are small, then they are invertible. Okay. Then I have to tell you what is the perturbation part of the output. And this is actually hard because you have to multiply, you exponentiate the perturbation part. So you get many copies of P1, many copies of P2. They can be connected with all those edges, and the edges can become chains of edges. So it's actually really, really hard. But when you think about it very hard, it boils down to stuff that has to do with connected Feynman diagrams, much like in ordinary quantum field theory. Or alternatively, you can write it as a solution of a certain messy partial differential equation. But, I'm writing partial differential equation, but everything is in the world of power series. So we're actually still completely in algebra. Okay, and everything has concrete formulas. Okay, so maybe I will not go into it right now. Okay? Yeah?
What is Alexander Ingalls? What was it?
And I should say two things. One of them is the answer to your question. So one is that just a warning. So this is the latex warning symbol, okay? So the Knuth warning symbol. So we're actually one abstraction level up from tangles. So you might be tempted to think that the invariant of a tangle will be somehow a morphism like this from the initial points of the tangle to the end points of the tangle. But we're one abstraction level up. We're not describing tangles, but maps between tangles. So a tangle is really a map from the empty thing to a thing that has strands. Okay? So a tangle will correspond to things that have only Latin letters. So objects that look like this in our category. Okay? And then if you have two tangles and you want to compose them, the way you compose them is you compose them using a multiplication operation. A multiplication operation is an operation that has inputs and outputs, so it will be a full DoPeGDO thing in our category. So composition of tangles corresponds to first multiplying them in the naive way, like product of quadratics, and then composing it with a certain operator that performs the multiplication. Okay? So we're actually, it's just a warning. Okay? Tangles do not, so like elements of the categories do not correspond, of this category do not correspond to tangles, but to operations between tangles. And the next thing I wanted to say is that if you just look at the first 4 lines here and ignore the perturbation, what you see is the Alexander polynomial. So the Alexander polynomial lives here. But it's not just the Alexander polynomial, it's a great abstraction of the Alexander polynomial. It's the Alexander polynomial generalized to tangles. Originally it's only for knots, but first of all we generalize it to tangles, and then we replace it by, and then we lift it to operations between tangles. So
which
yeah.
Lie algebra you need to take for that?
Epsilon equals to 0. Take the Lie algebra that I wrote before and set epsilon equals to 0. No, that's not SL2. That's the farthest away from SL2.
So it's a Borel part of SL2?
It's a two-dimensional Lie algebra semi-direct product. It's dual, where the dual is taken with a 0 bracket. Okay. So in fact, last time I spoke in Vietnam, I spoke only about this in a much more primitive version. Okay? I'm running out of time, so this was supposed to be the middle of the talk, and my debts to you at the middle of the talk were, why is it good for quantum algebra? Why is it good in knot theory? How does the inclusion of homomorphisms between quantized universal enveloping algebras into DoPeGDO, how does it actually work? Proofs that everything is DoPeGDO. So far I'm only making assertions, I haven't proven anything. I have to tell you something about relations with prior art, namely Rosansky and Overbay, maybe more. So I will not do all of that because I'm running out of time, but very, very, very quickly, so here is a statement in, so why is it good, what is it good for in quantum algebra? So here is a statement in quantum algebra. Some crazy thing defined using standard operations in Hopf algebras is a right integral or left integral on the quantum double of a Hopf algebra. The way we arrived with this theorem was by checking that it works in the abelian case, and assuming that something like it will be true in the non-commutative case. except in the non-commutative case, this formula that appears here has many variants. The multiplication could be from left to right, from right to left. This could be a left integral or a right integral. Everything becomes more complicated. And if you ever try to trace such things, you'll find that they're extremely difficult. You'll get confused and make infinitely many mistakes before getting anything right. So the trick for us would be to implement everything. Here is a full implementation. And then write a table of all possibilities and check each one if it's true or false. The moment the moment all morphisms become concrete morphisms, I can just check for equality. And then you'll find that in this whole matrix of possibilities, left multiplication, right multiplication, left bracket, right bracket, R matrix, the R matrix composed with the antipode, this whole huge array of possibilities, 2 give you a true answer, and then you get a theorem. Then I want to switch to why is it useful in knot theory. So, for example, if you wanted to compute the trefoil, you simply enter it into the program. So it's a product of tensors. So R matrix, R matrix, R matrix, a kink, a cap, and then you compose it with various multiplication operators, and you get an output. This is the invariant computed by this means of the trefoil. And then you can go ahead and tabulate it. And if you tabulate it, so here is a complete tabulation. Hopefully it's readable on your handout for the Rolston table. And again, it will take me a long time to tell you how to read it. I'll only say that it actually separates the Rolston table. And if you restrict your attention to knots with up to 12 crossings, which is as far as I've gone, I simply haven't gone farther than that, you get an invariant which is A, computable in polynomial time, and B, stronger than Homfli PT and Chovanov homology taken together. Okay? Stronger in the sense that it separates more. And furthermore, it has properties. So I've indicated here the amphichiral knots, and there is a property for amphichiral knots. If you look at it, you'll find that at least superficially it gives a genus bound, and indeed it gives a genus bound. And I truly ran out of time, and I wish I could tell you more. Well, Christian is already mad at me. I mean, I didn't have time to tell you why everything is DoPeGDO, but basically, for each of the objects in the huge matrix in the beginning, where is it? I know I'm out of time. So for each of the objects here, there is some clever argument why it is DoPeGDO, why it is of the relevant form, and you know, it would take a whole course to do it in full. I'll stop here, I'm sorry.
Thank you very much.
Are there questions or comments?
Yes, Ilya.
Please, invariant C mutation.
Sorry?
Invariant C mutation.
No.
No, it cannot. However, here I sort of perturbed SL2, okay? Had I taken a higher Lie algebra, it would see. Everything should generalize to arbitrary semi-simple Lie algebras, and then, I'm saying should rather than does, because we never worked it out. There isn't an implementation. There is a partial work for SL3 by a student of Roland Schaverling. No. I hope I'm pronouncing his last name correctly. Anyway, if it should it should be detect mutation if you increase the 2 here to 3. Yes? Effie?
Is for SL2, is it recoverable from the Carlow-Jones polynomial? The invariant, is it determined?
It is equivalent to the Color-Jones polynomial.
Like in loop expansion? What?
It is the loop expansion of the Color-Jones polynomial, but it is better in 2 ways. One, it is computable. The Color-Jones polynomial, with all due respect, is computable only for very small knots, and if you're lucky, slightly bigger. Okay, and this is computable in polynomial time, so in principle you can compute it for very large knots. And the second point is that it's a whole portfolio of things, and not just the invariant itself. It's not just the end product that is computable, but many operations that revolve around it. And well, I'm already way past time, but I could explain to you why this has no theoretic implications. So for example, the Color-Jones polynomial does not behave well relative to all of this portfolio. Even this would require an explanation. And the Color-Jones polynomial has nothing to say about genus. The reason our invariants have something to say, or the Rosansky-Overbay, or the loop expansion has something to say about genus, is because it is well behaved relative to all of these operations.
Question?
Stavros?
Yeah. So, do beads fit in this framework? Beads.
Yes.
They do, huh?
Yes.
I see.
But it's a long story.
Yeah, yeah.
Ilya?
Is there a connection to twisted Alexander polynomials?
Not that I know.
Other question? No. Let's thank Laura again. Red button. So let's talk in